We're good?
Yeah, we're good.
Okay, welcome back. Yeah, so I guess, what did we do last time? I guess we talked about the Bruja order, and I guess maybe I said things about it. I don't actually remember what we did. But I think at some point Mitchell asked a question about this subword property that I wrote, where I said there were these three equivalent ways of thinking about the Bruja order. One is the original definition, where you say, like, U is less than V if you can get from U to V by repeatedly applying reflection so that at each step the length goes up. But then there were these two equivalent conditions about subwords. One is saying that there exists a reduced word for V that contains a reduced word for U as a subword. And then the other one is there that for every reduced word for V, it contains a reduced word for U as a subword. And he asked, well, is this equivalent to just saying that some reduced word for V contains a word, not necessarily reduced, representing U? And I guess I blanked on this, but I shouldn't have blanked on this. I should have known this, because this is basically just a consequence of the deletion property. So the deletion property tells you that for any word representing U, it contains a subword, which is a reduced word for U. So the proof here is just the deletion property. So I'll remind you, the deletion property just says that if you have a word representing U, then you can find two letters, and if the length of the word is bigger than the length of U, meaning that it's not a reduced word, then you can find two letters in that word so that deleting them still gives you a word representing U. And so the point is you could just keep deleting these pairs of letters until eventually you get a reduced word for U. Okay, so that's just one thing I wanted to clear up. I guess another thing is I was not going to prove this equivalent characterization of the Bruja order in terms of cover relations. So I said, okay, there's the original definition where you say U is less than V if you can get from U to V by repeatedly multiplying on the right by reflection so that at each step you go up but in length. But you could also equivalently describe the cover relations. And we said a cover relation is just where so U is covered by V if you can get from U to V by multiplying on the right by a reflection so that the length goes up by exactly 1. And this is essentially saying that the Bruja order is graded, and the rank function is given by the length of the element. And so Ilaria asked me to prove this, so I'm going to go through the proof. I guess it's not actually that bad. I was going to skip it, but if you don't like it, you can blame Ilaria. But okay, so here's the lemma that we want to prove. Okay, so suppose we have some elements U and W in our Coxeter group, and we'll say they're distinct. So let's let S1 through SQ be a reduced word for W. That contains a reduced word for U as a subword. Then there is some element V such that the following three properties hold. First of all, U is less than V in the Bruja order. Secondly, the length of V is just the length of U plus 1. And some reduced word for W some reduced word for V is a subword of this fixed reduced word that we chose for W. So it's a subword of this S1 through SQ. Okay, and so notice that this will imply, if you believe the subword property, this will imply that you can have this grading of the Bruhat order by the length, because you can say, well, if U has a reduced word contained in this, then I can find this element V, which has length 1 bigger, and then I can just induct by saying, okay, well now I have this V and this W, and I could find some other element, say V prime, which is length 1 bigger than the length of V, and I just keep going constructing this chain where at each step I go up in the length by 1. Okay? So this should imply this equivalent way of thinking about the Bruhat order. So here's the proof. Okay, well, here we go. Of all reduced words, let's say S1 dot 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 SI1 hat dot 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 SIK hat dot 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 SQ for U. Okay, so remember what this means. It means I've taken S1 through SQ, this thing, and I've deleted some letters SI1, SI2 up to SIK. Okay? So among all such words, let's choose one such that IK is minimal. And then I'm going to let T be this element that I get by writing, okay, so I'm going to do SQ, then SQ minus 1, and so on down to S sub IK. And I'm going to go up to S sub Q minus 1, SQ. So this is some palindrome that I'm writing where I'm basically taking, okay, the last part here, but I'm including the SIK, and I'm reading it like backward and then forward. Okay, so it's like SQ, SQ minus 1, dot, 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 SIK, and then go back up to SQ. So this is some reflection, right? When I have one of these palindromes, this will be a reflection. So then, if I take UT, what is UT? Well, what I have written is that it is S1 dot 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 SI1 hat. So I've removed the SI1 dot 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 SIK minus 1 hat. So I've removed SI1 through SIK minus 1. But then I keep going and I don't remove SIK. And then I keep going and I have SQ. So it's essentially this thing, but I didn't remove the SIK. Okay, you can just, I think, check that if you take, where is my reduced word? So if I take this, this is a word for U. And if I just multiply it by T, you can see that this is what you get. Okay. So this means that the length of UT is at most the length of U plus 1, because this is saying that I have some word representing U. I've added one letter to it, which is SIK. This gives me a word for UT, so the length of UT should be at most the length of U plus 1. Okay. So claim is that the length of U is actually less than the length of UT. And if so, then setting V equal to UT proves the length. Okay, so why is this? Well, in this case, I am going from u to ut by multiplying by a reflection on the right, and it increases the length, if I believe this claim. So that would mean that ut is bigger than u in the Bruchal order, by the definition of Bruchal order. So u would be less than v. But because we know that the length of ut is at most the length of u plus 1, well, if it's actually bigger than the length of u, it would have to equal the length of u plus 1, so that would give this condition. And then we're saying that some reduced word for v is a subword of S1 through SQ. Well, that's again because there is a word for v, which is a subword of S1 through SQ. But then also, we have this thing that I mentioned at the beginning of class where if you have a word representing v, then it contains a reduced word for v as a subword. Okay, so we just want to prove this claim. So let's suppose instead that the length of u is bigger than the length of ut. So remember, when you multiply by, oh, maybe I haven't said this, but if you multiply by a reflection, so a reflection will always be like an odd element in the sense that you can write it using an odd number of simple reflections. So this means that the parity of the length has to change when you multiply by a reflection. So if the length did not go up, it had to go down. It couldn't have stayed the same. Okay. So okay, now we are assuming that the length went down, so we can use this strong exchange property. So by the strong exchange property, we have two possibilities. So either, well, maybe I should remind you, what does the strong exchange property say? It says that if you have some element and you multiply it on the right by some reflection and the length goes down, that means that you could have taken the word and just deleted some simple reflection from that word. So in other words, because of this, we have some word for ut, which is obtained from this word for u by deleting a letter. So let me write what the equivalent things are. So either t is or maybe another way of saying this is saying that t is a right inversion of u. And I said I know what all the right inversions are. Remember, I wrote this at some point. They're basically all of these palindromes that you can get. So this means t is one of these palindromes that you can get from some word for u. And hold on, where am I? Okay, so either t is this thing. All right, sq minus 1 dot 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 sp dot 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 sq minus 1 sq for some p greater than ik, or t is, okay, sq, here's why I didn't want to do this, dot 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 sik hat dot 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 sij hat dot 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 sr without a hat dot 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 sij hat dot 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 sik hat dot 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 sq. Okay, what is this? Oh, and I should say for some are less than ik with r not equal to ij. Okay, so well, what is this? I guess the point is t should be one of these palindromes that you can get by basically taking this this word for u and saying, okay, I'm going to go like from sq minus 1 all the way to some point, and then I'll go back. And if you go to a point that is like to the right of the sik hat, then you're in this situation. It's just sq minus 1 dot 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 sp, and then you go back. Or it could have been that you go to some sr, which is like between some of these hatted things. And in that case, it's where you have this sq all the way down to sik hat, dot 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 sij hat. So here I guess I'm removing all of the letters that are like sij, sij plus 1 all the way to sik. This is kind of a lot. But then we go down to the sr and then we go back. Okay. Hopefully this makes sense. I'm just writing one of these palindromes, and the two cases are, do I go and like, so I go some point and I go back, and it's like, do I stop to the right of the sik, or do I go past it and then go back? These are the two conditions, or two cases. Okay, so let's do these two cases. Case 1, which is this one. So I'm going to write w is the same as wt squared, because t is a reflection, so it is an involution. Right, anytime you conjugate, I mean, we know that the simple reflections are involutions, and if you conjugate them, you get still involutions. So what is wt squared? Well, we can write this as, first of all, w is S1 through SQ. That's what we started with. And then I'll write T as this. Wait. Why did I write it this way? Is that right? Oh, yes, okay, I'm going to use this. The point is, okay, this is T, but this is also T. So I'm going to use both of those. I'm going to say, okay, T is SQ minus 1, dot 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 SIK, dot 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 SQ minus 1, SQ. But T is also this thing, in this case. So I can write it as SQ minus 1, dot 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 SP, dot 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 SQ minus 1, SQ. And okay, well, what is this? Okay, what did I write? I'll write it down, and then we can try to make sense of it. So I said S1 dot 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 SIK hat, dot 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 SP hat, dot 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 SQ. And I think what this is saying, so like this is what's written in the book, and I don't know, you kind of have to stare at this and be like, okay, what actually are the letters here? Because the dot dot dots get confusing. So I think the point is that we have S1 through SQ, and then the SQ down to like this point cancels, and then you go back up. So now you're left with like basically S1 through SQ, but without the SIK. And then when you multiply by this, you're basically going to cancel the SP. Right? So this is essentially what's happening. You start with this word. When you multiply by this word, it deletes the SIK. And when you multiply by this word, it deletes the SP. Okay?
Can I make a remark
Yes.
about this? I think Yunso asked last class why it can't be the case that two of these right inversions that you get from taking the palindromes from the end can't be equal to each other. And this is why.
Oh, okay. So this is why two of these palindromes that we write down for the list of inversions are actually different.
Yeah.
Okay. Yes, thank you.
And if you already know that, that's another way of seeing why this is a contradiction.
Okay.
Because you have T written like that, but also like that.
Yeah. Okay, yeah. That's a good point. But we can simplify this to, or okay, what am I saying? I've written W as, so a different way of seeing the contradiction is W is now this word, where I've taken this reduced word and I've deleted 2 letters, but that can't happen because the reduced word is supposed to have the smallest possible length. But this is ridiculous, since the length of W is supposed to be Q. Case 2, so here I'm going to say U is UT squared. Okay, so we can write this as, S1 dot 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 SI1 hat dot 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 SIK hat dot 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 SQ. So this is the U, and that's because of this. Then I want to write T. So that is SQ dot 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 SIK hat dot 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 SIJ hat dot 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 SR dot 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 SIJ hat dot 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 SIK hat dot 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 SQ. Great. And then there's another, so this is one way of writing T, and the other way is just to write it as SQ dot 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 SIK dot 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 SQ. Okay, so that's this way of writing T, and then also this way of writing T. And similarly, if we simplify what this is, you'll find that this is S1 dot 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 SI1 hat dot 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 R hat dot 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 SIK dot 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 SQ. Okay, so right, because what we're doing is we're taking this word. Do I want to go through this? I mean, yeah, what is even happening? You get this somehow.
So the first application of T is removing the SR.
Yes, thank you.
And the second application is adding back in the SIK.
Yeah, exactly. So this is going to take this word and delete the SR hat, and this one is going to add back all of the S, so it's going to add back the SIJ, SIJ plus 1, all the way up to SIK.
I think just the SIK.
Or, wait, why not the J's? Oh, yes, you're right. Yeah, because this only goes down to SIK. Yeah, good point. Okay, so maybe actually to make this a little clearer, I should do this. IK. Yeah, good point. Okay, so this removes the SR, this one adds back the SIK. And this is a contradiction because we assumed that IK was minimal. Over here. We said among all of the ways of finding U, or a word for U, a reduced word for U as a subword of S1 through SQ, let's choose one that has the minimum possible, or a value of IK. And here's one with a smaller value of IK. So, wait, maybe I shouldn't, yeah. Maybe this should say like SIK minus 1. Okay. Anyway, this contradicts. the minimality of IK. Okay. Yes, it's a.
In Mitchellsburg, why is I keeping minimum one?
I mean, why is IK being like? Well, you want this contradiction, right?
No, in Mitchellsburg.
What is Mitchell's
What's
proof?
why proof? Like ahead of proof.
Oh, like you look at the two raised to rank T and then.
Oh, I think that was just for the first case, saying if you believe this fact that these palindromes have to be distinct, then you automatically get a contradiction once you've said that you can write T as this, but also as this. But I think that would not say anything about the second case, right?
Yeah.
Right. Okay. Okay, so are we good up to here? Let's go to the lifting property. So this is a nice property about the Bruhat order. It says, suppose U is less than W. So U and W are elements of my Coxeter group. U is less than W in the Bruhat order. And S is some left descent of W that is not a left descent of U. Okay, so what does this mean? It means that S is a simple reflection. If I multiply it by W on the, or if I multiply W by S on the left, the length goes down. But if I multiply U by S on the left, the length does not go down, and in fact it has to go up because of this parity thing. Okay, then, so I'll draw a picture of this. But here's the statement. Then U is less than or equal to SW, and SU is less than or equal to W. So the picture of this is we have W, and here's SW, and it's down because S is a left descent of W, meaning that if I multiply by S on the left, it goes down. And here's U. And here's SU. Because S is not a left descent of U, so if I multiply U by S on the left, the length actually goes up. And I'm assuming that U is less than W. So actually I have, maybe I won't draw it as a, just draw a little green line, so, or I'll do like a squiggly thing. So I guess this is my way of saying like U is less than W, but that would not be like an edge necessarily in the Hasse diagram. And so what the theorem is claiming is that we actually have I can't do this anymore. Something like that. Okay. So SU is less than or equal to W, and U is less than or equal to SW. Okay, so we can prove this. Proof. So let S1 through SQ be a reduced word for SW. Then, if I write S times S1 through SQ, this is reduced. This is just because S, like if I take U and I multiply by S on the left, the length goes up. So this is a word representing SU, and it has length one more than the length of U. So it has to actually be a reduced word for SU. Okay? So we know by the subword property that there exists a subword SI1 through SIK of this word. Or of of S1 SQ. Wait, sorry. This is SW. I think I was saying U. Okay, sorry. This is SW, and if I multiply by S on the left, it goes up to W. Sorry, so this is, I think I was saying U, but this is a reduced word for W. But it's the same reason, which is just that when I multiply SW on the left by S, the length goes up. Okay? So hopefully that wasn't too confusing. But this is a reduced word for W. But we know that U is less than W in the Bruja order, so there is a subword of this reduced word for W that represents U. And so it's this thing. So there's a subword, this, of that. That is a reduced word for U. Since S is not a left descent of U, SI1 is not S. Okay, so the reason is this is a reduced word for U. If SI1 was S, then if I multiply by S on the left, it would cancel the SI1, but then the length would go down. And we're saying actually no, the length goes up when you go from U to SU. But also, SI1 ... SIK is a reduced word for SU. This is what I should have said earlier, where SI1 through SIK is a reduced word for U, but if I multiply by S on the left, the length goes up, and that means that this is actually a reduced word for SU. And it is a subword of S. Wait, did I write that right? Okay, I think I wrote this wrong, but what I want to say, I think, is that it is a subword of this. S1 through SQ. Okay, so what are we saying here? We want to conclude that SU is less than W. Well, this is a reduced word for SU, and it's contained in this reduced word for W. So by the subword property, SU is less than W. We also want to say that U is less than SW, That should be because we have a reduced word. This is a reduced word for U. Oh, but it's also a reduced word for S1 through SQ. Right, so this is because, again, SI1 is not S. So actually, if I'm saying that SI1 through SIK is a subword of S1 through SQ, but the first letter here is not, it's a subword of S times S1 through SQ, but the first letter is not S, so actually it's a subword of S1 through SQ. Okay? Does that make sense? Okay, so hopefully this makes sense. Any questions? Okay. Let's let me define something for cosets. So let P be a coset. Then a lower bound, or respectively an upper bound, for two elements x and y in my coset is an element z in my coset such that z is less than or equal to x and z is less than or equal to y. So this would be for a lower bound, but then I'll write the respectively. Upper bound would mean that z is greater than or equal to x and z is greater than or equal to y. Okay. There's nothing terribly complicated here. It's just saying a lower bound is something that is below both x and y, and an upper bound is something that is above both x and y. Okay. So here is a proposition. Actually, I can write it here. Any elements, what did I call them? U and W in the Coxeter group have a lower bound and an upper bound in the Bruhat order. Okay, so part of this is very easy. So who can tell me why U and W have a lower bound? Yes, Yunza.
The identity.
Yeah, the identity is a lower bound for any two elements because it's below everything. So proof. The identity is a lower bound for U and W. Okay, but now we want to prove that they have an upper bound. to find an upper bound, let's induct on length of u plus length of w. Okay. So let's do the base case. If the length of u plus the length of w is 0, well, then the only way this can happen is if u and w are both the identity, and then, well, the identity would be an upper bound, or like actually anything else would be an upper bound. So then u equals w is the identity, and e is an upper bound. Okay, so now let's do the induction step. So let's assume that the length of u plus the length of w is positive. Then, without loss of generality, assume that the length of u is positive. Right, if the sum is positive, at least one of these has to be positive, so let's assume it's the length of u. Then, because u has positive length, it's not the identity element, so it has some left descent. Maybe I didn't justify why this is the case, but you can just write some reduced word for u, and then whatever the first letter you use is, that's going to be a left descent of u. So let S be a left descent of u. Then, by induction, there exists some element x such that x is greater than or equal to SU, and x is greater than or equal to W. Right, this is because SU has length less than U, less than the length of U, because S is a left descent of U. So if I use induction by replacing U and W by SU and W, I know that they have an upper bound, which I'm calling X. So one case is if S is actually a left descent of this element X, then U is less than or equal to X by the lifting property, and I'll explain why. So in this case, X is an upper bound for U and W. Okay, so how am I using the lifting property here? Well, I'm saying in this case where S is a left descent of X, I can draw this picture that I had over there where I have here's X, here's SX, here's SU down here, and here's U. Right, so this works because S is a left descent of X and it's a left descent of U. So I have this picture. But I know that X is greater than or equal to SU in the Bruja order. So I have my green cover, or not cover, just green relation here. The squiggly line. And so that means that I get these red dotted lines. And so U is less than or equal to X, which is what we want. Okay, so that's one case. That's where S is a left descent of X. So the other case, if S is not a left descent of X, then U is less than or equal to Sx by the lifting property. And I'll draw another picture for this. So in this case, U is less than or equal to Sx, but so I'm saying that Sx is an upper bound for U and W. Okay, so well, this would be because Sx is greater than or equal to U. Why is Sx greater than or equal to W? It's because, this is because, S is not a left descent of X. So this would say that, well, let me just write this here. We're just saying W we know is a left, or is less than or equal to X. But if S is not a left descent of X, then X is less than or equal to Sx. Okay? I guess one thing I'm using here is this fact that like the Bruja order is indifferent between left and right multiplication. So I'm going up when I multiply by this reflection on the left, and the length goes up. So okay, why is U less than or equal to Sx by the lifting property? Well, I just have to draw one of these pictures again. So we have Sx here, and here's X. That's because of this. And then down here, I'll have Su, and this is U. Just like before. And so I have this, right, because Su is less, why is Su less than or equal to Sx? Well, that's just because we know that, Su is less than or equal to X. Yeah, Su is less than or equal to X. Yes, thank you. Su is less than or equal to X, so it's less than or equal to Sx. And then we get the red dotted lines. Okay. Okay. Any questions up to here? Okay, so I'm going to say things about finite Coxeter groups. Finite Coxeter groups are nice because, well, they sort of provide a nice class of Coxeter groups to work with where special things happen. So oftentimes if you have like combinatorial things you want to do with the symmetric group, you can say, well, the symmetric group is a finite Coxeter group, so maybe I can prove something for other Coxeter groups, but maybe it's hopeless to look at like arbitrary Coxeter groups, because they could be like crazy and infinite and stuff, but you could say, well, maybe there's something nice about the finite Coxeter groups. Okay, so let's talk about finite ones. Okay, so here's a proposition. I guess I'm assuming for now that W is finite, but I'll say it anyway. If W is finite, then there exists an element called W naught. And this is standard notation, so often if you see W naught, that's referring to this element that I'll define here. So there's this element W naught in W, which is basically an upper bound for everything. So such that W is less than or equal to W naught for all W in W. Also, the left descent set of W naught is the entire set of simple reflections. This is also true for the right descent set, but for now let's just deal with the left one. So this is called the long element. Okay, so it's this very nice, I guess I should say, there are these special elements of your Coxeter group. Of course, there's the identity element, which is like some nice element that you should consider, but then also there are like the simple reflections. Those are special elements because they're generating the group with these relations. And when you have a finite Coxeter group, this is another very nice special element. So maybe I'll say this is, let's make this two parts. 1 and 2. If there exists some element W, or let me call it X actually. If there exists some X in our Coxeter group such that the left descent set of X is the entire set of simple reflections, then actually our group is finite. And this element is actually the long element. Okay, I think, yeah, we have time to prove this. Okay, so proof. Part 1. So this just follows from the fact that you can't have multiple maximal elements in the Bruhat order, because if you did have two maximal elements, like imagine I have my Hasse diagram for the Bruhat order, and it's something like, okay, I've got like a bunch of elements here, and maybe here's a maximal element, and here's another maximal element, and it's like, there's nothing above this, and there's nothing above this, so that's what it means to be maximal in this poset. Well, if that was the case, then we have this result saying that any two elements have an upper bound. So that would mean that there had to be some other element above both of them, but then they wouldn't have been maximal. So in fact, there has to be a unique maximal element of the Bruhat order in this case. Okay, so Bruhat order cannot have multiple maximal elements because of this this fact, since they would have to have an upper bound. I guess I didn't justify why the left descent set is all of, oh, okay, well why is the left descent set the set of all simple reflections? Actually, I can ask you. Yes, you so.
Because if not, you can multiply it.
Yep, yeah, so if it wasn't all of S, you could find some simple reflection so that multiplying by X on the left by that simple reflection moves you up, but then it wouldn't have been maximal. Okay, so that's 1. So now for 2, let me do it over there. Okay. So let's suppose, this is 2. Suppose that we have some element X such that the left descent set of X is all of S. We will show that U is less than or equal to X for all u in W by induction on the length of u. So, well, so the base case is if the length of u is 0, then, well, that's easy. Then u is just the identity, and we know that the identity is below everything. So then u is less than or equal to x. So now let's assume that the length of u is positive, which means that we can find a left descent of u. So let little s be a left descent of u. Then SU is less than u because it's a left descent. So SU is less than or equal to x by induction on the length. Right? We're proving by induction that everything is below x, since SU has smaller length. This means that it has to be less than or equal to x. But then since S is also a left descent of x, by our assumption that the left descent of x is all of the simple reflection, or the left descent set of x is all of the simple reflections, we can use the lifting property. So the lifting property says that u is less than or equal to x. So let me draw the picture again. Here's x. S is a left descent, so we have Sx here. Here's u and Su, because S is a left descent of u. We know by induction that Su is less than or equal to x. And now we get this, these red dotted lines. So u is less than or equal to x, and that completes the induction. Okay? Oh, maybe I should, okay, before doing that. So this shows that everything is less than or equal to x, but then we know that an interval, so this means that W is just the set of all things, it's the interval between the identity and x, but this is finite, because remember we said that whenever you have some element, you can give an upper bound of 2 to the length of that element for the number of things below it in the Bruhat order, because they're just the things that you can get by taking subwords of a reduced word for x. Okay, this is finite. Now, I guess I'll just remind you that the size of this interval is at most 2 to the length of x. Yes.
Is that W not W?
Sorry? What?
Oh, never mind.
Mm-hmm. I think I saw a paper on the archive like 2 days ago about like computing the sizes of intervals in the Bruhat order, possibly for like infinite Coxeter groups, but like this is not an easy thing to do. But we can give an upper bound in this case. It's at most 2 to the length of x, but in general it's like not obvious what the size actually is. Okay. Any questions? here are some properties of this long element W naught. So I don't think I'm proving these. I didn't write proofs. But here are just some properties. One is that it's actually an involution. So W naught squared is the identity. That's cool. Another fact is that the length of W times W naught, so here W is just some other element, this is the same as, well, the length of W naught times W, and this is just the length of W naught minus the length of W. Another fact, the length of W naught times W times W naught. Notice here, this is just conjugating W by W naught because this is really the same as, well, I could put an inverse there, but it's the same because according to the first bullet point, W naught is its own inverse. So I actually don't need to write the inverse. But this is just equal to the length of W. If I take the set of left inversions of W times W naught, this is the set of reflections minus the set of left inversions of W. Let's see, is that right? I want to make sure I got the order right. In the case of the symmetric group, okay, let's talk about the symmetric group just so I can check if I'm making a mistake or not. What is W naught in the symmetric group SA? Yes.
Like n minus 1.
Yeah. So it's the decreasing permutation that goes n minus 1, ... 3, 2, 1. If I multiply W by W naught on the right by the decreasing permutation, you can check that this just reverses the one-line notation of W. So if I start with W and it's like, I don't know, 4, 1, 6, 3, 5, 2, then to multiply by W naught on the right, I just reverse that string of 6 numbers. And so if I had a left descent of this, that would be some pair I comma j, so that I is less than j and they appear out of order in this. But that's saying that I and j appear out of order in the reverse of W is the same as saying that they appear in the correct order in W, and that is what this is saying. So this is correct. Does that make sense? So this is the set of this is the set of pairs I and j that are in the wrong order in W. So when I take the complement, this is the set of pairs I and j that are in the correct order in W. But being in the correct order in W means that is the same as being in the incorrect order in the reverse of W. Okay. One other thing is that, okay, what is the length of the long element? Well, it's the same as the number of reflections. And in fact, the inversion set, either the left inversion set or the right inversion set, will just be the set of all of the reflections. So actually we can say something a little more. So we have this, so I'll say the maps sending x to x times W naught. So the map that just, it goes from our Coxeter group to itself and multiplies each thing on the right by W naught. And well, there's also the map that sends x to w naught times x. These are anti-automorphisms of the Bruhat order. Okay, what is an anti-automorphism? Well, remember, an isomorph or an automorphism of a poset is just a bijection from the poset to itself that preserves the order relation. An anti-automorphism is going to be a bijection from the poset to itself that reverses the order relation. So this is just saying that these maps are bijections. Okay, it's obvious that they're bijections because you're just multiplying by an element of a group, and so the inverse is just multiplying by the inverse of that element, which in this case is actually the same element. And the reason, so what I'm saying here, anti-automorphism, this is just saying that x is less than or equal to y if and only if x w naught is less than or equal to y w naught. But that's also if and only if w naught x is less than or equal to w naught y. And so one other thing that this means is that if I take my Bruhat order and I multiply everything on the right by w naught, that is an anti-automorphism. But then if I multiply everything on the left by w naught, that's another anti-automorphism. If you compose these, you get an isomorphism. So the map that sends an element x to w naught times x times w naught is an isomorph or an automorphism. Of Bruhat order. Maybe I should write down explicitly what I was saying for Sn instead of just saying it verbally. So in Sn, W naught is this decreasing permutation, which is n minus 1, dot, 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 2, 1. Then W naught, or so, X W naught is the reverse of X. Is there better chalk? I might just write in yellow or red. I'll just write in yellow. Okay. So in Sn, W naught is the decreasing permutation. X W naught is the reverse of X. W naught X is sometimes called the complement of X. And then W naught X W naught is sometimes called the reverse complement of X. The way I like to think of this is, remember we have a way of representing a permutation with a plot, where I said just plot all of the points I comma W of I, so you get this arrangement of points in the plane representing your permutation. When you reverse it, all you're doing is you're just reflecting about a vertical line. And when you take the complement, you're reflecting about a horizontal line. And when you take the reverse complement, you're doing a 180-degree rotation. But here I can give just some examples. So let's take x to be 4, 1, 6, 3, 5, 2 in S6. Then if I do x times W naught, this is just, well, I reverse it, so I get 2, 5, 3, 6, 1, 4. If I do W naught times x, the complement is basically replace each number with 7 minus that number. So 4 gets replaced by 7 minus 4, which is 3. 1 gets replaced by 7 minus 1, which is 6. 6 gets replaced by 1. 3 gets replaced by 4. 5 is replaced by 2. 2 is replaced by 5. And then if I want to do W naught x W naught, well, if I was thinking in terms of the plot, again, that's rotating 180 degrees. Or I could just say it's just reversing this thing. So it would be 5, 2, 4, 1, 6, 3. Yes, Yunza?
Does that bijection any nice pattern avoidance sense?
Oh, like does it behave well with pattern avoidance?
Yeah.
Yeah, I mean, this will behave like if x avoids the pattern 2, 3, 1, then the reverse of x will avoid the reverse of 2, 3, 1, which is 1, 3, 2. And so these dihedral symmetries, yeah, they behave well with pattern avoidance in that way. Is that what you're asking? Yeah, okay. Yeah, so in general, if sigma contains tau, well, that sigma will contain tau if and only if the reverse of sigma contains the reverse of tau, and that's if and only if the complement of sigma contains the complement of tau, and so on. Okay. Let me just mention one more thing in the last couple minutes. So in the Bruja order, the elements covering the identity are just the simple reflections. Right, they're just the elements that have length 1, which are just simple reflections. So, since this map, which is basically conjugation by W naught, is an automorphism of the Bruja order, it should send the simple reflections to themselves. So, this map sending x to W naught, x, W naught, this is an automorphism, well, it will map S to itself. It'll be basically a permutation of the simple reflections, but actually it's an automorphism of the Coxeter graph. And I guess I'd have to say what this means. It's a bijection from the vertex set of the Coxeter graph to itself, and it preserves adjacencies, and when it preserves adjacencies, it also preserves the labels on those edges. Maybe I'll say more about this and give more examples next time, but for now I'll just leave it at this. That's all.